Okay, we're recording. So, okay, I think you all
I just
know
wanted
Mano,
to do a
so
brief.
I will turn it over to Mano, who's from Case Western Reserve, and Mark would always announce that he was the director of the University Center for Innovation in Teaching and Education, USITE. So I'll turn it
And he's
over.
also done, Mano moved to the Monterey area in late 2019, but he was with us and did all a really nice assortment of different presentations on different topics between the years of 2009. And I think your last one, Mano, might have been 2018.
Yeah, that
As
sounds
I
good.
remember. That
Yeah.
was on, it was a pretty mind-bending one on Einstein. I can't remember the exact title.
It was a crash course on Einstein's general theory of relativity in 1 hour.
And it was excellent, as were all of your presentations. And they weren't always science-y stuff, okay? He gave a really good one on the Greece versus Galloway Supreme Court decision from, I believe that was back in 2013 or something like that. So
been a while.
Anyway, great to have you back, Mano, and we're going to hand it over to you.
Okay, so I'm going to share the screen and let me know, and I'm going to put up the slides. Let me know if things are a problem. Is that okay?
Yeah, because everybody can minimize everybody's faces and all that. So yeah, all you got to do is minimize that. I've got it full screen.
All right, so this talk is based on a book that I published that appeared in December of last year, really this year, and it's called The Great Paradox of Science. And as you can see, the subtitle on the cover of the book is White's Conclusions Can Be Relied Upon Even Though They Cannot Be Proven. My subtitle, all through the writing of the book until almost the very end of the publication process, is what's on the left, which it says, White's theories work so well without being true. So it's different. So what happened was the other theory, the White works so well without being true, was what I was trying to say, and the publisher was fine with it, but at the very end, I heard from my editor that the publishers had got together and they were a bit worried about that subtitle, because there are people who take things out of, they quote mine, they take people who are opposed to the conclusions of science, they take things out of context and then use it. And they were worried that the people who oppose scientific conclusions, in, anti-vaxxers or anti-evolutionists or climate change deniers, might seize on the thing about theories not being true and say, aha, scientific theories are not true, and ignore the first part, which is White's theories work so well. So they wanted to change it. And so the final thing on the cover was the compromise we agreed upon. But I just wanted to say that the original one, I think, is better. It's more direct. But that's how it goes in the publishing world. You have to respect the publishers and their concerns as well. So one thing we can be sure is that science really works well. It works extremely well. And it's so much a part of our lives that we take it for granted. And this cartoon, which is in my book, I'll let you read it. Can you see the cartoon and read the?
Yes.
So you can see this is a senator grandstanding against science. And I let you read it. I like the one that points to him and says he's alive 50 years past the expiration date, thanks to science. And, he has had wrist surgery and a smartwatch. And yet he says, don't listen to science. What science ever done for us? And it also reminds me of that scene from Monty Python's Life of Brian, which I'm sure all of you have. I hope all of you have seen it. If not, you're missing a treat. There's Reg, the John Cleese character. He's trying to encourage his followers. I'm getting some feedback. Is there some?
Yeah. Somebody must have. I don't know who it is. Everybody should mute their microphones. Let's see.
Okay, I think, let's see. Yeah, it seems to be fine now.
Okay.
So Reg, trying to incite his followers to rise up against the Roman occupiers, asked, what, apart from the aqueduct, sanitation, roads, irrigation, medicine, education, wine, public baths, freshwater system, law and order, public safety, and peace, have the Romans ever done for us? And that's kind of like what people say about science. They always ask, what has science done for us, forgetting what all the things that it has done. So why is science so successful? Why has it been able to achieve such great success? And it's tempting to think that surely it must be because its theories are telling us something true about the world around us. Oops, I'm again getting some feedback.
It looks like Valerie's name keeps popping up with the echo.
Okay, but the history and philosophy and sociology of science suggest there is little reason to think that the reason that science is so successful is because it is telling us something true about the world around us. Okay, so let's ask the question: what exactly is science? The problem with trying to define science is, while people have tried to do it for a long time, trying to identify what exactly are the characteristics of science, there has been no satisfactory demarcation criteria. In other words, both necessary and sufficient conditions have not been found to define science. But there are two necessary conditions. Scientific theories must be naturalistic. In other words, there must be no appeals to the supernatural. And another one is that they must be testable. Any scientific theory must make predictions of new observable phenomena that we can look for. And these are fundamental. Okay, so we cannot, as a result, we don't have necessary conditions, we don't have sufficient conditions, so we cannot say if a theory is science. But we can always say if a theory is not science, if it is not naturalistic, and if it's not testable. And this cartoon that some of you, I'm sure, have seen, a famous Sidney Harris cartoon, illustrates the point about naturalism. So there's this complicated long proof, and then in the middle it says, then a miracle occurs. And this scientist saying, I think you should be more explicit here in step 2. So you cannot allow miracles in science. The evolutionary biologist Richard Lewontin said, we cannot live simultaneously in a world of natural causation and of miracles. For if one miracle can occur, there is no limit. If you allow even one miracle in science, then there's nothing to stop anyone from claiming that some funny result that they get in their laboratory or in their experiments is due to some miracle. And in fact, this is the fundamental problem with intelligent design, is that it never made any testable predictions, and it was not naturalistic. It was a miracle theory. And that was why it was never accepted as a science, even by scientists who were religious. Because scientists know that within science, you cannot have theories that are not naturalistic or not testable. So I want to pause at this point to ask, because this talk is going to be a fairly long argument, and I want to let people let things sink in before moving on to the next stage. So are there any questions at this point that people have about anything I've said so far? No? Okay. Let's move on. So there is what about something called the scientific method? So those of you, I mean, all of you probably have been through the ordeal of science fair projects as school children, or been the parents of children who have had to do science fair projects, and they will learn something called the scientific method. And it consists of 7 steps in a sequence. You posing a research question, conducting background research on the topic, constructing a hypothesis about what you're observing, conducting experiments to test the hypothesis, analyzing whatever data you get, and then using that analysis to draw conclusions about the validity of the hypothesis. Have you confirmed the hypothesis or disproved the hypothesis? And then once you have got those results, you communicate the results in the form of a talk. or a scientific paper. So that's what we normally call the scientific method. And you'll see this sort of written in various places. But that is not how scientists actually work. Scientists, what they do, how scientists actually work is they use all those 7 elements, but not in any particular order. Okay? They're usually, scientists are just messing around. They're trying things, discarding things, and so on. But what they use various heuristic, what are like rules of thumb, methods to pick and choose which of those elements to use at any given moment. So usually it starts with the scientist getting some sort of idea about something. They may observe something that's funny, or they might see a connection between one thing and another that they had not noticed before. And then they get an idea about what might be going on. And so they try something out. And then they do some research to see whether there's any work that has been done on that. Based on that research, they may try something out. Based on the results, they may decide, well, it's not going to work. Let me look at the research some more. And then they may try something else out. Then they may postulate a new hypothesis, go back and forth. So science is usually that kind of thing, jumping around these various elements and using what you would call an intuitive sense of what might work best at any given moment. They are not following a prescribed list. They're jumping around. Whichever works at any moment is what they use. It is only at the very end of the process that history is rewritten with that neat order. So when the scientist has completed the work and arrived at some sort of satisfactory conclusion, they go back and write a history of what they did, and then they will write it in that form, in that sequence, because that's a kind of traditional form. And this rewriting, so whenever you read a scientific paper, it's almost never an accurate reflection of what the scientist actually did. It's a reconstruction of the historical record. And this is well known, and scientists know this. Scientists know that when what they read in the paper is not the order in which it was done, but the final cleaned up conclusion of the process. Okay. And there's a nice article by Peter Marawa, this famous scientist, who talks about why scientists rewrite history in this way. So as I said before, science works exceedingly well. And it also seems to show continuous progress, getting better all the time. Okay. I think you cannot deny that the science we have now is better than it is in the past. If you go back 500 years ago, you would find a very primitive world in which the scientific theories in use at that time were much worse in terms of their effectiveness than what we have now. Okay? And so why is it that science keeps showing progress? And the most plausible theory is that science must work so well because its theories are true. What do we mean by true? Well, we believe that there is a world out there, what we call reality, and that the theories of science that we have are trying to represent or understand that reality as accurately as possible. And that's what we mean by true. A true theory is one that is an accurate representation of the outside world, nature, if you like. But even if we haven't quite reached an accurate representation, it is plausible to believe that the reason science shows progress is because it is steadily approaching that reality. If we are getting close to the truth, even if we are not there yet. Okay? But unfortunately, there is no reason to believe that either of those things are true. That either that the theories we have are accurate representations of reality, or that they're even approaching that reality. So that means that we have to ask ourselves, how can we explain scientific progress? What is it progressing towards if it's not progressing towards truth? Because when we think of progress, we think of it as a goal-directed thing. That is progressing, you're always progressing towards something. But is that the case? Well, it seems like in the case of scientific progress, it is not progressing towards truth. So what are the common beliefs about science? One is that scientific theories make predictions. Remember, I said that's one of the necessary conditions, that scientific theories must make predictions that can be tested. Then we believe that you do experiments to test those predictions. If experimental results agree with the theoretical predictions, the theory is confirmed or becomes more probably true. And if the experimental results disagree with the theoretical predictions, the theory is falsified. This is a common framework in which even among the scientific community, you will find people believe this. Okay? But again, like most other things in this area, things are not so straightforward. The reality is quite different from that. And the reason is the following. When we talk of experimental results, what exactly do we mean? In its raw form, the raw data consists of something like a click on a Geiger counter, some sort of reading on a meter, tracks in a bubble chamber, some piece of mechanical information that we get. By itself, that has no meaning. Okay, the reading on a meter is just a reading, it's just a pointer reading on a meter or the digital reading. So in order to make sense of that, you have to have interpretive theories to translate this raw data into physical quantities. For example, if you're looking at the theory of evolution and you find a fossil or you find some bone somewhere, a bone is just a bone. It's a piece of mineralized material. It has no meaning in itself. In order to make it into an observational or experimental result, you have to interpret that piece of that object. Try to find out what its age is. What animal did it come from? What kind of lifestyle did it have? Now, in order to get all that information, you have to bring in a whole lot of other theories, interpretive theories, to translate that raw fact, that raw piece of data into something that you can make meaning out of, into physical quantities. And when we do that, we have to draw upon all kinds of background knowledge that all the other theories use to extract information from the raw data. So experimental results are not just raw data. We may talk of them as if they are raw data, but they are a mixture of all these three things involving theories. And the same thing is true for theoretical predictions. When we say that a theory makes a prediction, we are never using just a single theory. What you have is what you call the basic theory or theories. In the literature, sometimes they call it a hardcore theory. That is what we are focusing on. But we also have thing called the initial conditions. And we have various auxiliary hypotheses that are needed to actually implement the theory. And then we also have what I call escape clauses, which we say with all other things being equal. So for example, if you want to explain a theory, if you want a theory of how the earth originated, we have a theory that it started out as a gas mass. So you have to have the basic theories, the gravitational forces, and that are acting on these gases that form the earth. But you also need initial conditions. How fast were these gas particles moving? What was the state of motion? Then you have various auxiliary hypotheses that are needed to actually implement the theories. So for example, you need to think about how the energy, when the gas compressed to form the solid, how did the heat dissipate? Where did the heat go? What are the properties of the early earth, and so on. And we also have to assume that nothing has changed from the time the initial gas existed to now. So when we make a theoretical prediction and say, okay, based on this theory, we believe that the earth should be so many years old, it's not just one theory involved. There's a whole host of 4 components that go into that theory. Okay. So when we say we compare the theoretical prediction with the experimental result, what we are doing is we are comparing a theoretical prediction package of a lot of theories with the experimental result package of a different set of theories. And if they agree, all we can say is that we have some consistency among the items, not that the theory is confirmed or more probable. But more importantly, if they disagree, we cannot say that the theory is falsified, since the theory that we are working with is just one of many theories involved in this comparison. So we cannot really talk about falsification as a definite thing. And there is a nice example. Most people tend to think of the scientist as analogous to a watchmaker. This was an analogy brought forward by the philosopher of science, Pierre Duhem, about over 100 years ago. And he said, when you take a malfunctioning watch to a watchmaker, the watchmaker can take each part out and test it independently, the little cogs and the wheels and so on, and the springs, and test each part independently of all the rest until the watchmaker, she finds the one part that is not working, and then can replace that part with a better part or a new part and make the watch work. And we tend to think of scientific testing of scientific theories like that. We can take each theory, test it independently, see if it works. If it doesn't work, we can replace it with another theory until the whole system functions well. But Duhem says that the scientist is not like a watchmaker. He can't work like a watch. She can't work like a watchmaker because, and the scientist is actually more like a physician. Now, when you go to a doctor saying that you don't feel well, she cannot, and you think, she may think it's your heart, but she cannot just pluck the heart out from the rest of the body and test it independently. She cannot take the kidney out. She cannot take the lungs out. That each part of the body is connected to every other part of the body. And you have to examine it with all those connections. As a result, you cannot really definitely say which part is the problem. You have to make an inference. You have to weigh a lot of factors and say, ultimately come to the conclusion that maybe the most likely problem is the heart or the lungs or the kidney or the liver, but you cannot test it independently. And Duhem's point is that when a scientist is working, she is more like a physician in how she operates or how she has to operate than she is like a watchmaker. She does not have the luxury of separating out each theory for testing. Okay. As a result, because of these limitations, science cannot prove theories to be true. And science cannot prove theories to be false. All scientific theories are underdetermined by data. What I mean by this is, however much data you may collect, you will never have sufficient data to conclusively prove a theory to be true or false. It cannot be done. I mean, I haven't elaborated on this in this talk, but that is the case. You cannot prove theories to be true because theories are always underdetermined by data. However many data points you have, you can construct an infinite number of theories to fit that data. And you cannot eliminate them just by the data. Another thing is that scientific facts, what we call scientific facts, are not unchanging objective statements about nature, but are theory-dependent judgments. A scientific fact is not a fact in the sense that my table here is a fact. It's a judgment made on the basis of data because of all these factors. Okay. For example, in my book, I have a long chapter about the age of the earth. And I show how calculations about the age of the earth have changed dramatically over time. Starting from almost prehistory to now, they have oscillated between being infinitely long to being very short, to being long again, to being short again, and to the current time. So why does the age of the earth, which you might think of as a simple fact, how has it changed? It changed because the theories we use to understand the age, to analyze the age, those theories changed over time. And as the theories changed, the age of the earth also changed. Okay. As for falsification, in history, when you look at the history of science, we see that scientists, although they may talk about falsification, they never actually use falsification to eliminate theories. For example, Newton's theories were disagreed with the motion of the perihelion of Mercury, with the perigee of the moon, with the motion of Uranus. They disagreed for about 60 years. Technically, Newton's theories had been falsified because there were observations that didn't agree with the theory for decades, multiple decades. But scientists did not say, Newton's theory is falsified, let's get rid of it. Okay, and that's because although we may talk of falsification as an idea, in practice, scientists never actually use falsification to eliminate theories. And that's good, that's a good thing. Because if you think about it, every theory always has results that don't agree with it. Whatever theory you're talking about, you will have disagreement with some result. That's always the case. And if you've used falsification, if you said that a theory has to be discarded if it is proven to be false, every theory would be discarded. You'd be forced to discard every theory as soon as it is invented. You would never have any theory. So it is a good thing that falsification is not used in practice, even though it has great appeal as an idea. Okay, I have said some things that I think might be unfamiliar to people. So I'd like to pause at this point and ask whether anyone has any questions.
I want to remind everybody that if you click on participants, you can raise your hand, and I'm watching it right now, and you can unmute yourself after that, and not seeing any hands raised just yet.
Okay.
No, nobody
Okay.
yet.
I just think it's, I don't know, it's not really a question, but I just think it's fascinating when you said like scientists just kind of mess around. Because I have this conception of a scientist being very rigorous and like you have to follow the rules. And so it's kind of heartening to say that it's a little improvisatory. So.
There is a lot of improvisation.
Yeah.
And
that sort of plays to the quote I put up in the chat, which was a marvelous piece by Isaac Asimov, which says the most exciting phrase to hear in science is the one that heralds new discoveries is not eureka, I found it, but that's funny.
And that's why, if you talk to any scientific research group, there will always be controversies and discussions and arguing amongst about, well, what does this mean? And what should we do next? And what if we try this? But the other person will say, no, I don't think that's going to work. Try this instead. And, if there was a rigid prescription, you wouldn't see that. Actually, there's
Jeff Hess has a question.
What?
Jeff Hess has a question.
Okay, go ahead.
You can go ahead and unmute, Jeff.
Okay, got it. You mentioned earlier that when the papers are produced, that not everything is there. The scientist is writing a history of what they did, and they leave out things that may have been dead ends. Yes. And I'm wondering do people ever have access to what those dead ends might have been? Because those could lead to other conclusions, other realms of experimentation.
Yeah, very often, yeah. That happens through private channels. So what happens is, this is where conferences and private channels, when scientists present at a conference, the most interesting discussions take place in the hallways afterwards, where their colleagues who are working in similar areas will ask them, so what about this? Or did you try this? And they'll say, yeah, we tried this, it didn't work for these reasons. Or if you are another research group and you are interested in their work, you contact them. And scientists are almost always willing to share with them all the things that didn't work. But they don't put those in the papers because scientific papers already are too long and complicated as it is. If you included all the things that didn't work, you would have each paper would be like an encyclopedia. And there's another reason, though, that I think they're not included. There is a strong belief in science that it's the end result that is important, not the journey. And so the question is, once you have arrived at a conclusion, that conclusion is important. How you got there is less important. So the only people who are interested in how you got there are people who are doing similar research who want to save some time by avoiding the same paths that you took that were unfruitful. Okay.
I have a comment. What about incompleteness of a theory? It doesn't necessarily invalidate a theory if it's incomplete. Specifically, if I was a theologian and I wanted to critique evolution, the thing I would comment about is biogenesis. And as far as I know, we don't have much of a theory of biogenesis. So I would argue that, well, clearly there must be something that started life, even if it evolves through natural selection. So what about an incomplete theory?
Well, in a sense, all theories are incomplete because they always have unanswered questions. Now, the theory of evolution is, I mean, it doesn't really deal with abiogenesis, the actual origin of life, right? Theory of evolution deals with how life evolved after it was created. The theory of abiogenesis is something else. And there are different people who work on that. I mean, there's a whole host of research groups who are trying to understand how life might have originated at all. So if people ask me about what about abiogenesis, how does it affect the theory of evolution? My answer would be it's nothing to do with the theory of evolution. It's to do with the theory of abiogenesis. And then you can look at all the literature on the research that's being done on that area. You know, under what conditions did it form? Or could it have formed? Do those conditions exist now or at the origin? At the time that the Earth was formed, the conditions were very different. The atmosphere was very different. The heat and the light was available was quite different. It's hard. It's a hard problem, but there are people working on it, and there's quite a lot published on that.
Well, you can say it's unrelated and a different topic, but evolution presupposes biogenesis, doesn't it?
Evolution by natural selection requires an existing organism to work. You know, you have organisms that work by natural selections, competing for resources. And the initial creation of that life form is not strict. It is incomplete. Evolution, you can say it's incomplete because it doesn't deal with it. Another way to say it is not that evolution is incomplete, but it's like saying evolution is incomplete because it doesn't explain the origin of the universe. Yeah, you need the universe to be created to create life and so on. But you're really getting far away from the original intent of the theory. And evolution is not really like that. It's a different field of study, abiogenesis.
Okay. Fair enough.
All right. So the central question is, if, as I have said, the comparisons between theoretical predictions and experimental data can neither confirm nor falsify theories, why bother to do them at all? I mean, why do we do experiments to test theories if they don't seem to prove or disprove theories? What purpose do they serve? And this is important. The results of these comparisons are what constitute evidence in science. It is evidence, this evidence that is used in evaluating the merits of theories. Okay? How scientists work. Scientists use various heuristic methods, again, rules of thumb, that consist largely of testing theories and revising them on the basis of the resulting evidence. As I said before, individual scientists act more like physicians than watchmakers. They are doing experiments, but trying to interpret them in the context of all the other theories. It is the scientific community as a whole that works like a panel of judges, weighing the evidence and arriving at a consensus verdict on which theories and paradigms to accept and which to reject. So there's a difference between how an individual scientist works, like a physician, and the community of scientists. And it is the community, not individual scientists, that make judgments about theories. And what they do is they weigh the evidence and arrive at a consensus verdict on them. And that can take a long time. And it's an informal process. It takes place, it's not like the Supreme Court that they meet, a group of scientists meet and decide which theories to accept or not. It's an informal process. And the consensus, but even though it's informal, the consensus is very strong. Once the community of scientists has decided, for example, that they want to use the theory of general relativity instead of Newtonian gravity. That pretty much sets the framework for how future science is done. Once they decide that the theory of special relativity is what they want to use to analyze things as opposed to Galilean relativity, that consensus pretty much determines how science progresses. So although it is an informal consensus, it is much more powerful than the formal consensus that you get in a legal setting. In order to arrive at that consensus, scientists use what they call scientific logic. And here, this is important. Scientific logic, there's one thing is the burden of proof. In science, we sometimes want to know about the existence of things. You know, is the COVID-19, is it a virus or a bacteria? Is it, you know, you want to show that it exists and there are certain qualities. And one of the rules of science is that if you want to claim the existence of something, that existence claim is presumed to be false unless there is a preponderance of evidence in favor, or its existence is necessary as an explanatory concept. So if you want to claim, for example, if you want to claim that anything exists, you have to provide a preponderance of evidence. If you don't provide that, that claim is presumed to be false. So that is why we can ignore the existence of fairies and mermaids and the Loch Ness monster and unicorns and all that, because however much people may want to believe them, there is no preponderance of evidence in their favor. And in using scientific logic, we can say these things do not exist. The fact that we cannot prove them to not exist, which is what some people, their defenders will say, is irrelevant. In science, if you do not have positive evidence in favor of an existence claim, that existence claim is assumed to be false. Now, there are some cases where we give provisional existence. And that is if something is necessary as an explanatory concept. For example, ether was long believed to be in existence, not because we had any positive evidence for it, but because it seemed to be necessary in order to explain how light propagated through the empty space through the vacuum of empty space. So it was a necessary explanatory concept. Now we never, similarly it was true for neutrinos. Neutrinos for a long time had no positive evidence for their existence, but they were a necessary explanatory concept. The same is true with the Higgs boson, which was believed to exist for 50 years before it was actually positively identified. So what happens is we can assign a necessary as an explanatory concept. We can say this is necessary, but that is a provisional existence. With the case of neutrinos and Higgs, we actually got positive confirmation evidence. But in the case of ether, we didn't. So why do we believe that the ether doesn't exist? It is not because we proved it did not exist. We can't prove that ether does not exist. But why we think it doesn't exist is when Einstein came along with his theory of relativity, he made the ether unnecessary as an explanatory concept. So since there was no positive evidence for it, and it was no longer necessary as an explanatory concept, we now can confidently state the ether does not exist. That's how we show existence or non-existence.
Mano, can I
Sure.
ask a question?
Sure.
I'm just curious, based on what you just said, would something currently in the news regarding science, would the concepts of dark energy and dark matter be examples of the explanatory concept that you're talking about right now?
Exactly.
Okay.
Right now, we give them provisional existence because they seem to be necessary explanatory concepts to explain certain observed phenomena. We haven't observed them directly. So yeah, so we have to wait and see. Two things can happen. One is when experiment might actually directly detect them, in which case they cease to be explanatory concepts and become entities whose existence we have confirmed. That's one thing. Or a theory might come along that makes them unnecessary. For example, there are alternative theories like modified Newtonian dynamics that say that we don't need dark matter. Now, those theories have not been accepted as part of the scientific consensus. But if at some point in the future there is an alternative theory that explains some of this data without dark matter or dark energy, then we would say that dark matter and dark energy do not exist. But right now we are in that gray area. Okay?
Yes, thank you.
So universal claims are presumed to be true, conversely. So if you take a law of science, like the law of conservation of energy or momentum or whatever, we assume that the universal law claims are true. We presume to be true unless you find some sort of existence claim that violates it. So to prove the law of conservation of energy to be false, you have to find some result that contradicts it. And there has to be a preponderance of evidence for that. Something else is that negative evidence plays a critical role in scientific logic. And what I mean by negative evidence is the things that you do not see. And that's important. For example, I think all of us believe that there are two kinds of charge, positive and negative. And there are no other charges. How do we know this? How is it that we are so confident of this particular fact that our entire modern world is built on it? The answer is we have not proved that to be true. We cannot prove that to be true because there's no way we can test all the charges in the world to see if there are only two. Excuse me. So why do we believe so firmly that there are only two charges? And it's because of negative evidence. And what I mean by that is, we find that if we take any three charges, say A, B, and C, if A and B attract each other, and if A and C attract each other, you will always find that B and C repel each other. And you can explain this result by assuming that there are just two kinds of charges and that there is a law that says that like charges repel each other and unlike charges attract each other. Any set of three charges that we have show this same result, and therefore we say there are only two charges. If someone were to come along and say, well, there might be a third charge, that person would have to show experimental results that violate this pattern that I just showed you. As long as that pattern holds, that minimal assumption there are two charges and they follow this law holds true. That is why we believe that there are only two charges, not because we have proved it to be true, but because there is no evidence that contradicts it. There's another thing called logical contradiction that can rule out some existence claims, but I won't get into that. So how science progresses? New evidence in favor of and against the existing paradigm is constantly being generated and evaluated. And based on such evidence, scientific consensus verdicts can decide that an old paradigm should be replaced by a new one. So that's how scientific theories changes. The community of science decide by some sort of consensus that an old theory is no longer working well and should be replaced by a new one. That's how Newtonian laws got replaced by Einsteinian laws. That's how the phlogiston theory of oxygen got replaced by the oxygen theory. That's how the Ptolemaic astronomical system got replaced by the Copernican system. All these things, that's how they came about. Okay. I'm now going to talk about how paradigms change. And before I get to that, are there any questions? Because this part is a little bit more philosophical.
Jeff,
It's only hand by Jeff. I don't know if that was from the old question or not.
Who?
Yeah, Jeff, do you have a question?
No? Okay.
No? Okay.
All right. Here's a figure. And let me explain this. I'm going to talk of paradigms as a framework, scientific framework built around a particular theory. And let's think of the Newtonian paradigm, which consists of Newton's laws of motion and so on. And a paradigm I'm representing by this kind of hairpin bend, a hairpin. And all the area inside the hairpin consists of experimental results that agree with that paradigm. And all the areas outside consists of things that disagree with that paradigm or have not been tested. We don't know. So there's an infinite number inside and an infinite number outside. So let's take Newtonian mechanics. So as I said, there are always what we call anomalies, experimental results that disagree with the paradigm. And let's say that in this case of Newtonian paradigm, there are two anomalies, experimental results, X and F. And say, let's X be, say, for example, the motion of the perihelion or Mercury or anything. So now there's a problem because you have a paradigm here and results that don't agree with it. And much of science consists of trying to resolve these contradictions. So what they will do is experimentalists will work hard to try and do better experiments on X to see whether they can get X to move into the under the hairpin. In other words, to bring it into agreement with the paradigm. Or theorists will try to work with the paradigm and tweak it and make modifications and so on to see whether the hairpin can be extended to include X. So much of scientific research is trying to reconcile these anomalies, trying to bring the experimental result and the theoretical paradigm into agreement. But sometimes that will not work. And this is a persistent problem. What happens is at some time you get a new paradigm being proposed. Say in this case, it'll be general relativity. And that overlaps with some of the old paradigm results. There'll be some, by the way, can people see this little cursor that I'm moving around? Do you see that? Do you see the cursor?
Yes.
We see it.
Okay.
Yes.
Okay, good. So there'll be some overlap between the old paradigm and the new paradigm, but the new paradigm might explain X, which is what general relativity did. It explained the perihelion of Mercury, but it didn't only do that. The new paradigm predicted a new result, Y. In this case, say the bending of light by the sun, which would never have been considered under paradigm A. It was not even thought of. But the new paradigm B predicted that. Because of factors like this, the community of scientists decide that, okay, we think paradigm B is the better one for the future. And so the community shifts from paradigm A to paradigm B. Once the community has shifted, they treat X as a falsifying event. X was not falsifying for the decades before paradigm B was proposed. It was just considered an anomaly. But once paradigm B is accepted, X is rewritten, is reconsidered and treated as a falsifying event. And similarly, after that, there might be a new theory that comes along, a new anomaly for the general theory related, new anomaly, and things might shift to paradigm C, and from there to paradigm D, and so on. But remember, the reason we went along this sequence of paradigms is because of X that triggered that way. But the question is, there are always other anomalies, which for whatever historical reasons were not considered. And so you might have gone from A to paradigm B, and then from B to Q, from Q to R. There is an entirely different sequence of paradigms that could have followed. But the one that we took happened to be this one. But there were many other alternative pathways that could have been gone. And so, but history is written by the victors. After the community of scientists has shifted allegiance to a new paradigm, a process that can take years, sometimes decades, the history is written, especially in textbooks, by advocates of the new paradigm, and what used to be considered a mere anomaly, that X point, is elevated to the status of a falsifying event for the old paradigm. So the community tries to justify its shift from the old to the new by creating falsifying events. Hence, paradigm shifts are always seen as progress, just like with political revolutions. And I think this is Thomas Kuhn made this very perceptive identification. When you look at political revolutions, let's take the American Revolution. So the American colonial people there revolted against the British, made a revolution, and they overthrew the British, and they created a new country. Now, when they write the history of America, of course they will write that as progress. They will say the revolution was a good thing. What we had afterwards is better than what we had before. You never have a situation in any revolution where the people who won the revolution say, yeah, we won the revolution, but really what we had before was better. That never happens. History is written by the victors and always written in such a way to justify the change. And the same thing is true with scientific history. Textbooks always rewrite the process to show that what happened was progress. That's why we always have science progressing, not because there's any objective measure of progress, because the community requires it to be progress. They write it as progress, always. Okay. And so, what in agreeing upon a paradigm, scientists do not accept a finished product. They do not say this is the last thing. Rather, they agree to accept as a basis for future work and to treat as illusory or eliminable all its apparent inadequacies and defects. In science, there is no basis for validation superior to the collective contingent judgment of the paradigm sharing community itself. So what Barnes is saying is, it is the community of scientists who are the ultimate arbiters of what constitutes the correct paradigm, not experiment or anything like that. It's a consensus judgment, and that judgment is what determines what we think of as correct science. Okay, I'm now going to shift a little bit and show why there could be different evolutions. In Darwin's theory, book on the origin of species, he had only one figure, a very schematic figure of a tree. And this is a much more color, it was a pure black and white, very simple tree. This is a much more colorful tree, but the basic idea is the same. You start at the bottom. Here is where the origin, we talked of abiogenesis. This is where the original archaea and the bacteria started. Then they started evolving. As they started evolving, they branched off. You get different branches going, and then they branch off again and again, and they keep branching until, and these are new species that are formed along the way until you get to the canopy of the tree, all at the top. And the canopy consists of all the current species, humans, chimpanzees, dogs, ducks, crocodiles, whatever. All the living things that currently exist are represented by points on the canopy. All the species that went extinct early on are represented by the tree ending somewhere in the inside. So Darwin used the tree as a metaphor for how life evolved. Is that clear? I mean, are people familiar with that? So I am going to borrow heavily from Darwin's metaphor. And this is what I call the tree of scientific paradigms. Remember I spoke in that other figure about how scientific paradigms changed? So here we can say this is in the early days of science where there were just one or few paradigms. Then as science evolved, they started branching off. You get new fields being created, new theories being created to explain different things. They start branching. You get things like then physics becomes a branch, chemistry becomes a branch, biology becomes a branch, astronomy, and so on. And so it goes on, and they keep branching and specializing and so on until finally we end up with all the areas of science that we currently have on the canopy of science. So physics, chemistry, biology, geology, paleontology, and all the subfields. Along the way, some theories and paradigms went out of fashion. They ceased to exist, like phlogiston, ether, Ptolemaic astronomy, Aristotelian dynamics. Those theories can be represented like extinct species somewhere in the interior of the tree. So scientific paradigms evolve like life evolved. And the important thing to note is that this tree keeps growing. In other words, it progresses. This canopy will grow and grow further, but it's not growing towards anything. It's just growing. So science is not growing towards the truth any more than when life evolves, we are not evolving towards some perfect representation of our species. Humans are not evolving towards human perfection. We're just evolving. We're just changing. And dogs are not evolving towards the perfect dog. They're just evolving into different dogs. And the same thing with scientific theories. We are not evolving towards any perfect theory or towards some truth or whatever. We're just changing. Now, I am now going to talk about take this tree, and I'm going to say, take the entire tree and treat it as just science. So here, I call it the tree of science. So science, the entire constellation of science goes like this. And at some point, we make a paradigm choice. So we choose one paradigm over another. At that point, science as a whole goes in one direction, like this. Then we take another paradigm choice and it goes in another direction, like this. And then it make another paradigm choice, it goes like that, and like that, and like that, until we end up here, which is the current science on the earth. So what do these other branches represent? They represent the paths that science would have taken if at some point we had chosen a different path. In other words, if we go back, if we had gone along this other path, science as a whole would have looked different. So we might have gone along a different path. So all these other points on this canopy represent possible alternative science histories. In other words, they are sciences that could have occurred but didn't because we took particular choices along the way. So these are alternative science histories that are not realized. They are virtual science histories that we can only imagine. So the conclusion is that current science is not inevitable. The process is historically contingent. What we have now is the result of decisions made by the community of scientists all along the way from the distant past. And if we ran the clock again, if for some reason we could run the whole process again, just as the biological organisms that evolved would be very different from what we have now, so could the scientific theories also be very different. We have no guarantee that what we have now is inevitable. But how can this process be compatible with science progressing, getting better with time? What can science be progressing towards, if not towards the truth? This is the question we asked earlier. And the problem is that we think that science works, is able to be successful, predict and control events, must be due to our theories being true. That's the assumption we make, which I think is erroneous. The reason why science works has nothing to do with it being true or not. Science consists of consensus judgments made by credible experts using comprehensive bodies of evidence that are systematically acquired and evaluated using scientific logic and that pass through institutional filters such as legitimate peer-reviewed publications. This is what makes science work so well. Not because it's true or other. A key question: if extraterrestrials visited the Earth, supposing tomorrow a spaceship lands with beings from God knows what planet, they would clearly have technology superior to ours because they've been able to do interstellar travel and we haven't. The question of interest is, would they have the same scientific theories as we do? And so supposing you say yes, supposing you believe that they would have the same theories, then what you're really saying is that the true theories are timeless and universal. They are the same everywhere in the universe and they're unchanging and just lying about like fossils waiting to be discovered. Okay, that's what a yes answer would be if we found that they had the same theories as we do. But if the answer is no, if they are able to achieve this vastly superior technology with completely different scientific theories, that means that scientific theories are inventions that are neither true nor unique, but context and history dependent. We can't test this on Earth. Unlike with biological specimens, we have different continents that were separated from each other, and so species could evolve separately and independently of each other. In the case of science, science is like a gigantic invasive species that has taken over the entire planet. We just have science. Science on the Earth is just one science. Everybody across the globe uses pretty much the same science. We don't have the luxury of testing on Earth different scientific paths like we have in biology. So the only way we can see if there's a difference is by looking at different planets. Unfortunately, that's not an experiment we can run. We are not able to do that. But this is what yes and no means. But scientific history suggests that the answer is no, that we really have no reason to believe that the theories are timeless and universal, but that they are contingent and history dependent. And it should be sufficient, I think, for us that science works so well. The questions of truth are irrelevant and a distraction. I claim that it's a distraction. I end with this quote from Thomas Kuhn, which I think is very nice. He says, "Can we not account for both science's existence and its success in terms of evolution from the community state of knowledge at any given time? Does it really help to imagine that there is some one full, objective, true account of nature, and that the proper measure of scientific achievement is the extent to which it brings us closer to that ultimate goal. Okay. Thanks. That's my talk.
Thank you, Mano.
I hope if you want more details, the book deals with all that, so you can buy that and read it.
We can open it up to questions and discussion. So, well, maybe everybody can unmute as long as everybody doesn't talk over each other.
Well, that's really interesting because recently I remember somebody saying that if you destroyed the Bible, in 500 years you'd have a completely different religion. But if you destroyed books of science, in 500 years you would have the same science. And you're suggesting that it's not that way. I guess I don't really understand. I would think that some science is objective, and perhaps some elements could be invented. Is that true? Don't you think there's some objective elements of science that are just mathematical facts and would be repeated?
Yeah, I've heard that. And for example, I heard a scientist say he can't imagine at a conference, he said he can't imagine a situation where water would be anything other than H2O, right? Water would always be H2O. And the question is not necessarily, because when we think of hydrogen and oxygen, they are concepts that were invented to explain certain phenomena back in time. So the reason it looks like we have certain facts now that are unchangeable is because we are locked in to a whole network of theories that were decisions that were made in the past that took us along. Let me put it, get back here. The tree of scientific. So we, at various points, scientists took decisions that took us along to particular points on this canopy. Now, it's hard for us to imagine a completely different framework that depends on different decisions taken at a different time. So for example, if back in, say, 400 years ago, somebody had decided that phlogiston was the better theory for whatever reason, or found some alternative theory, they would have arrived at a different point, and they may not have the concept of oxygen and hydrogen that we have. Water might still be there, but the explanation in terms of H2O might not be there. This is hard to get our minds around because we are exposed to just one science on the earth. We have no difficulty in imagining species other than humans because we see them all around. We see dogs and cats and crocodiles and whatever, things that have evolved differently from us, right? Because they experience different historical conditions on different continents or different environmental nature. So we have no difficulty thinking of other biological species other than us. But we have no similar comparison with other scientific theories other than the ones we have and we have.
Marie has a good question she put to the chat. Okay, it's a two-parter. Okay, question. How would we postulate an alien theory of science? That's the first part. Second part, is mathematics not the language of the universe?
Mathematics is also what I would call axiomatic, okay? And when we say mathematics, what we call modern mathematics is based on a set of axioms that are assumed to be true and rules of mathematical operations. Now, the big question in mathematics is whether if the axioms are true and the rules of logic, mathematical rules of logic used are valid, then the theorems are true. In other words, then they would be universal. But as was shown by Gödel and other people, you cannot show those axioms to be true, the axioms of mathematics. So what the mathematics that we have is dependent on the axioms that we start out with. And as a simple, so if you have different set of axioms, you can have a different result. For example, 1 + 1 is 2. But that 2 is if you use the base 10. But if you use the base 2, 1 plus 1 is 10, right? On base 2. So whatever mathematical results we get will depend on what base you use, the simple arithmetic result. And as an analogy, so yeah, mathematics is not necessarily universal. We can't prove that it is universal. It depends on the axioms that are used. And we use a certain set of axioms. And it, as I said, the net result, the net thing that we look for is what works. And if things work, we assume that that is sufficient. But can we extend from that to saying this is true? That conclusion cannot be justified.
Then part 1 of the question would be, how do we postulate and, wait a minute, let me read it again.
Oh, by the way, I discussed this mathematics thing in the book too, because that's what she raises is a very important question.
The first part of it would be, how would we postulate an alien theory of science?
We can't. It would be like, I mean, science fiction writers try to do this. They try to imagine what an alien civilization would look like. But it's such a vastly open question that it's hard to create an entire, I mean, when you look at the complexity of science that we have now, it's hard to create out of whole cloth a completely different, consistent scientific framework. I mean, I can't do it. I don't know how anyone would set about such an ambitious task. That's a problem. We are so limited in our experience of alternative scientific theories because the science that we have has taken over the entire Earth. If it had been so that different continents on Earth had evolved separately and were not in touch with each other, we might have had a different science in South America and North America and Africa and Australia and New Zealand and so on, because they didn't communicate with each other. But science has just swamped the what we call Western science, has completely taken over the entire world. As I said, it's like a highly successful invasive species that has destroyed any other science that might have ever been created. And so we have it, and it's great. It works really well, and it's wonderful, but it prevents us from even imagining an alternative.
Okay, Ray asked, okay, and I assume he's referring to the mathematics question. He asked, how is what you said about that different than postmodernism? In other words, no matter what base 10 or whatever you're using, would not the calculations, say the calculations that send a probe, can send a probe from here to Jupiter and hit on a dime practically and do everything they plan it to do, no matter what base style method of mathematics, would not the calculations show the same thing?
Oh, there's no question that science works and mathematics works in that it can make tremendous predictions and achieve great things. We have achieved great things. That's not the question. They work. The question is can they only work in one way? And let me get back to the tree of science. This is, say, the current science, and these are possible alternative science histories. A metaphor is that to think of science working is the ability to shake this tree. I could shake this tree by holding on to this point, which is what we have. We have the current science on Earth. I can grab hold of that point and shake the tree and make it do what I want. But I could just as easily do that by holding onto a tree somewhere here and shaking the tree. I could still control things. But there's no reason to think that this point on the tree is better than that point on the tree. It might have turned out that, just as in case of biological evolution, if the conditions had been different in the past and evolution had taken a different path, we might have ended up with, as human beings, with fewer diseases, for example, no cancer or something. We don't know. It's hard to imagine, but it's possible. Just like that, it's possible that we could have arrived at some different scientific theories that enable us to do different things. There was that science fiction film that came a few years ago. blanking, but it was based on a story by Ted Chiang called Story of Your Life. And there they had, what was it? Marie?
Arrival, based on
Arrival. Thanks, Marie. Yeah, you're exactly right. Arrival. I'm not sure how many of you saw it. It's an interesting film to see. And basically, this turns out that these extraterrestrials, when they arrived, there were two problems. How do you communicate with them? You know, because they obviously don't speak English or any of the local Earth languages. And what is that? What are the scientific theories? The story, Ted Chiang's The Story of Your Life, which is available for free on the internet, is actually better. It goes into more depth. But basically, the idea is those extraterrestrials have different scientific theories from ours. And because it's a different scientific theory, they learn science differently. They are able to do things that we cannot, such as travel across time. The methods that they use for scientific analysis are so different from us that it enables them to get control of travel through time that we don't have. That was one of the few science fiction films that I saw that dealt with this question of how a entirely different scientific framework might enable you to arrive at entirely different results.
Randy, go ahead. You wanna? He's got a question on text, but he's also got his hand raised.
Oh, was my hand raised? I didn't know it was raised.
Yeah.
No, the question I had, I think he may have addressed it. It was kind of an observation I thought I had when he was talking about the differences in science. All of our science fiction, whether it's written or visual, appears to assume that whatever aliens we would encounter, they've discovered the same science that we have, went along a relatively similar path. And I was just curious if you developed a movie or a science fiction story in which they went along an entirely different, unfamiliar path, would we humans be able to understand the story or understand the movie we were seeing?
It would be very, very strange, yes. And as I said, it boggles the imagination to be able to think that. But the fact, we should not think of our present science as unique simply because we lack imagination. Okay? We should not mistake the paucity of our imaginative skills to suggest that therefore there is only one science that can exist. The evidence does not persuade me, at least, that the science that we have on Earth is unique. Just as the evidence does not persuade me that the biological species that we have on Earth are unique. If you have another living things in other planets, there is no reason to think that there will be anything like us. And we are comfortable with that. And the reason we are comfortable with that is because we have seen different biological species on Earth. So the idea of extending it to a completely different species on another planet is fine. But we have not seen different scientific structures on Earth. And that limits our imagination.
Lauren, you want to go ahead with yours?
Yeah, thank you. Yeah, my question, I'll just read it off the screen here. Would it be possible to have an alternative science that would have an alternative explanation that is as functional as the science we use? See, I'm an engineer, and I have sort of a, and it's flippant, but I think it's very true. If it works, use it, and if it don't, lose it. And I have, in that regard, I have to be extremely pragmatic. I mean, perhaps I didn't come up with Ohm's law, but I depend on it as, or I used to, as a retired electrical engineer. I depended on it on a daily basis. And it is, to me, the foundation upon which modern electronics is based. I can't imagine an alternative that would be different from Ohm's law and yet somehow as functional.
Things like Ohm's law, Newton's law, all these laws, they are the product of certain decisions made by scientific predecessors. For example, we chose to define resistance in a particular way. We chose to define voltage in a particular way, current. And these decisions were connected, but they were not forced upon us. These are choices that were made at a particular time in the past. And that resulted in giving us the form Ohm's law, V equals IR, that we now have. If different choices had been made in the past, what the properties of resistors and so on might be expressed in different formulae. For example, and they might look very different. They might still be functional. I mean, you would have different, it might still be functional. You'll be able to work with systems and design computers and so on. But the formulas that you use to understand those would be different.
Yeah, I'm certainly, I can see that, but mostly you're still talking about physical devices and physical, things, flow of current, the potential behind it, and the resistance to it. I mean, there may be differences in terms of scale or terms of dimensions, but the physical manifestation still hasn't changed. What may change is our perception of it or our approach to it, but the physical manifestation itself is unchanged throughout that. So,
depending on what you mean by physical manifestation, the wires you'll still have wires, maybe. But how you describe the properties of the wire will depend on the theories that you use to construct that understanding. So you may use concepts different from volts and currents and ohms. You might have completely different concepts. For example, if you had defined the resistance is defined as the ratio of the voltage over current, provided that remains the same for different voltages and current. But that's not the only way to define a property. You know that you can things called conductance, which is 1 over a resistance. Mm-hmm. And that's a simple transformation, and we can go back and forth from resistance to conductance. But again, that's because it's still based on the earlier decisions about voltage and current. But if we had a different theory of electricity from the beginning, if we didn't start out with the theories of electricity that we have now, we would have a different understanding of the properties of materials. And we may not have things that look like Ohm's law, or even, of course, not called Ohm's law, but they would still enable us to build stuff with it. They would just not look the same way we do. It's just like asking, would the extraterrestrials have Ohm's law? And I say there's no reason to think that they would have Ohm's law. They would probably have vastly superior technology, but it may not look like Ohm's law.
Rafiq, you want to go ahead?
Hey, Rafiq, where is he?
I'm here.
Hi, Rafiq.
Hi. I'm just interested in really the basic concept of, okay, it's the scientific community who are deciding on these things. But I'm just wondering how disinterested they are, in fact. I mean, we've heard a lot about peer review and some of the problems of peer review, that it might not actually be as good as it might otherwise be. And, a lot of the practical time that researchers spend is begging, basically. Instead of writing papers, they're writing funding applications and spending an awful lot of their time on that, hoping to get money to do what they want to do. Do you think that, in a way, money might have replaced miracles as being the spanner in the works? Anyway, because what you said is very interesting, but it is really a little bit theoretical when we come to how actually science works. Okay, that's my...
Well, I think you're right. I mean, what you're saying, what I was trying to say is that historical development of science is contingent. It depends on what factors influence the scientific community at any given time to choose one paradigm over another. Now, I didn't go into the details of the factors, but you have pointed one is money. For example, governments now spend a lot of money on research. And if they say, we want to put money into this area, the scientific community will make decisions on what they are going to study based on those decisions. And so that's why these government funding agency or funding agencies have a lot of sway in how science evolves, because they can guide the direction in which it goes. So you are absolutely right. Other factors that influence which paradigm win, it could be the prestige of the institutions involved. It could be the prestige of the scientists involved. Over time, I mean, that's why the community of scientists is important. And it is never the case that individual scientists ultimately make the decision. It's always the community. Now, the community itself might be composed of people, and there have been people who have said that the communities themselves are not fully representative of the overall scientific community. The decision-making scientific community does not adequately represent the overall scientific community, and that's a valid criticism. That's why increasing the diversity of the scientific community to make sure it's represented well, all the communities, is important, because that enables us to make sure that the consensus judgments that we arrive at are more valid than maybe otherwise. So yeah, money is definitely a factor, but prestige is also a factor. There are other factors that come. That's why I'm saying that the decisions are never uniquely thrust upon us by nature. These are always decisions made by people, and those decisions could have been different in the past. It should have resulted in different science now.
Dale, you want to go ahead? Or Dale and
Your
Wendy?
question, Rafiq?
It's me, Dale.
Hi.
Is someone else talking?
Rafiq, were you going to say something?
Yeah, I mean, there's only one thing, just a slight observation. And you said when something becomes interesting, there was a slight typo in one of your slides. Instead of why bother, you said who bother.
Oh, I should check that. Okay.
No, because I think that is really very interesting, and I think you've got a very good. That's something worth pursuing, and that was really the point that I was making.
Okay.
Thank you.
All right. I have two questions. The first one might be similar to the one Lauren brought up. I'm just wondering if it'd be possible for someone to go back to the bottom of this tree and follow a different path along it to come up with a different science?
Someone wouldn't be able to. You'd have to create a whole new planet with different. So it's not an individual journey. It's a community of scientists that has made this journey.
And another question before I go. What's after everything you've said, what's then the difference between citing scientific consensus to support an argument and the logical fallacy of an appeal to authority?
Because science works. It enables us to do stuff. Other belief structures don't work. I mean, as was pointed out before, science has, from the early slides, science simply has succeeded in creating so many successful things in our life, from medicines to technology to travel and so on. It's not an appeal to authority, it's an appeal to what works. Okay. And ultimately, what works is what drives scientists. Scientists, by the way, do not follow any philosophical framework. As Einstein himself said, a scientist is not bound by any philosophical framework. Scientists go where the evidence takes them. And sometimes that means ditching one philosophy and adopting another, ditching one theory and adopting another. As I said, they're always messing around, trying to find what works. And that single-minded focus on what works is what has made science successful, not any particular philosophical framework. So,
Marie has a comment there. Marie, you want to unmute yourself and elaborate? Are you a writer?
Oh, yeah, I write science fiction.
yeah, Marie writes science fiction. I know that. Yeah, how are you?
I'm doing good. And I'm really excited because I think that in a way I've been asleep on the job by not considering alternative to our presumed scientific theories, our assumed axioms, and that is a blind spot, which I think a lot of science fiction deals with addressing blind spots and saying, wait a minute, there are other ways to do things. So I'm excited about this.
Actually, Marie makes an interesting point about science fiction. So the people who use their imagination most are the science fiction writers, right? So they try to think of what if things are different. But it's interesting that what we call the good science fiction writers, quote unquote good, like Arthur C. Clarke or Isaac Asimov, are those who change things the least. They try to stick as close as possible to existing science. I am saying that maybe Marie could be the person who does this. Just completely break free from the existing and try to imagine a completely different scientific structure and what it might look like. To be quite honest, I don't think I could ever come close to doing that. It's just requires far too much imagination, much more than I have. But science fiction writers, I think, should be bolder in the alternative. I think Arrival was one of the few things that I saw that tried that a little bit.
Or just start with one science maybe and just think that, like, if they have a completely different idea of mathematics, that's easier in a way. And I've seen writers do different base units and so on, but to have, like, if we can say like chemistry, or they're like, oh my gosh, you guys base observations on like visual matter? What? I don't know.
You could even start with simple things like the circumference of a circle is tau d instead of 2 pi r.
Yeah.
And I feel like,
and break from there. I wanted to mention Afrofuturism and the Afrofuturism movement in science fiction today, where people imagine different cultures dominating and what the world would look like. I mean, most people are familiar with the wonderful Black Panther movie, but the idea is maybe Shuri's technology is so outlandish because it's based on a completely different beginning.
also learned what the Westerners do.
Right. But I love that argument that our science is a invasive species that takes over completely, because it's true. And I think it's built that way because it flagrantly steals what works, right? And discards what doesn't. And it's consensus based. So
I do fear it also destroys things it just doesn't like.
And there could be amazing scientific discoveries that could have happened if we hadn't. And this would be an interesting thing for alternate historians.
Yep.
Anthony, you want to elaborate on your comment? I think he's referring to a particular slide. Maybe he's not there anymore.
No, I think my point was made.
So Ray's got a question.
Oh, all right. Well, what you're proposing seems pretty radical to me. It's hard for me to wrap my mind around this because I thought science was not a convention, it was a convergence where we are closing in on the truth, not just inventing things. Now, we have religious beliefs that go on for centuries. And what happens with religious beliefs is they fracture over and over and over. And you're saying that, well, there's only one science. It seems to me that if what you're saying is true, we have all kinds of competing sciences, competing theories, all equally valid, vying for supremacy. So what would keep science going along in the same direction and everybody in the globe, regardless of their political or language or anything else, on the same page? Why is science all agreeing?
Because it works. If you
Because
want,
it works.
if you want an alternative science, you have to show that it works as well as the science that we have now.
But you're proposing that there are other
There could be.
paradigms that would work just as well then.
Sure. And if people, that's what I was telling Murray, if people can invent such a complete framework, alternative framework,
Well,
that
like
works as well as or better than the current science, that would be great. But I'm saying that that's a monumental task, much harder than inventing a different religion.
Well, Lauren brought up the very simple electronic V equals I over R.
Right.
And that seems very fundamental. I don't see how you could come up with an alternative to that was any more accurate. It's so simple and works so well.
Except that it's V equals I times R.
What's that?
He's saying the formula you quoted is V equals IR. Not
I over R. Didn't I say that?
No, I times R. But that's okay. But I know this. It's like how can water be anything other than H2O? How can resistance be anything other than VOR? But what I'm saying is that when we say something like that here, that's because way back people have made all kinds of decisions about charge, what constitutes electric charge, how they behave, and so on. And all those were decisions that took us along this path so that now we have V equals IR. And because we can only see the little space around where we are, we think that's all it could be. But if we had gone somewhere else, we wouldn't have concepts like voltage or current or resistance. We would have different concepts that relate to each other in different ways.
Well, if they were just as valid, wouldn't they have evolved? So you'd have some scientists pursuing this path, valid, and somebody over here pursuing another paradigm that's equally valid, and you would have competing theories.
Okay, let me ask you this question, Ray. How is it that humans have evolved differently from crocodiles? Why aren't we all humans or all crocodiles?
Well, because all you need to do is survive. It doesn't have to be one single organism. As long as you can survive and reproduce, you're going to be a valid species. And so the same thing would be for scientific theories, as long as they validly describe the universe and they work. If there's other ways to describe electricity besides what we just said, where are they?
Okay, but that's because at various points, these branches split off. So we went on the branch for humans like this way, and the dinosaurs went off in a different direction. Because at some point, there was a branch and certain things branched off this way and evolved accordingly, and the others evolved differently. And so now we end up at different points, and dinosaurs are very different from humans and other species. But that was purely because of chance, and there's conditions that existed at that time. So there was some sort of mutation and the biological conditions at that time favored certain branches going this way and other branches going that way. So we now have different things. And I'm saying that's an exact analogy to how science evolves. And so just as much as we can, why don't we have long tails like dinosaurs? Why is it that the dinosaurs have tails and we don't? Why is it that we walk on two legs and the dinosaurs don't? The crocodiles don't. It's because we evolved differently. And just as much as it's hard for us to imagine what it would be like to be a crocodile, and the crocodiles may not be able to imagine what it's like to be a human, but we both exist because we took different paths on the thing. And they each function perfectly well. Crocodiles function perfectly well in their environment. We function perfectly well.
Okay, may I step in here? It just, pardon my obsessing about the whole Ohm's law thing, but I mean, that was a pure observation.
No,
and as we've said the one thing that I've heard reinforced, and I think it's absolutely valid, is that the laws we're talking about are not prescriptive, they're descriptive. They're the result of observations. Mm-hmm. And if they're the result of observations, I'd still like to know what the mechanism could be to take an observation as fundamental as that and come up with a completely alternative description that is as functional and as valid as Ohm's law.
It's the observation, it's how you describe the observations. You may say, I see things in a particular way. I see things. But how do I describe those? In order to describe the observations, we need a vocabulary and a set of concepts. And those vocabulary and the concepts are based on historical antecedents. And if the antecedents had been different, we would still see the same phenomena, but we would describe them differently using different concepts and different forms. I mean, for example, you take, yeah, go ahead. So there is the fact that you can see the same things doesn't mean they have to be described in the same way.
In the biological tree of life, what constrains the development of organisms is their environment. But and what would be the analogy of the environment in the other tree that the tree of science?
Because science always takes place in a social context, right? I mean, scientists work within a certain time and place. So they have the political influences, their religious influences. For example, why is it that people thought that the age of the earth was 6,000 years at one time? I mean, that was because the context in which they lived, they did not have any independent sources of data. So what they used to arrive at their theories was what they had at hand, like the Bible and so on, and they made their theories. So science always takes place in a social context. It's influenced by the politics of the time, the economics of the time, the technology of the time, all these kinds of things. And if the contexts were different, they might have made different decisions.
But they were wrong about the age of the earth back then.
But what I'm saying, when you say they were wrong, they were different. When you say they're wrong, the reason we think that what we have now is right is because we have used a whole network of theories. The age of the earth that we arrive at now is due to a convergence of theories in physics, chemistry, biology, paleontology, and so on. But those theories themselves are inventions. Now you might say, why is it, okay, you're saying the age of the earth was wrong then. It's right now. How do we know that we are living at the time when we have got things right?
Right.
How do we know that?
Is it functional or isn't it? Can again, to use basic scientific theory, can you use this model to predict other behavior? I mean, as an example, I heard this story a long time ago regarding the discipline of physical chemistry. I've forgotten which element it was, but there was an element in the periodic table which had yet to be isolated in the field. But there was a gentleman who was an expert in physical chemistry who described what based purely in the theory of physical chemistry, how that element would react, how it would, what it would react to, what it would, it's basic chemical behavior based on the theories of physical chemistry. They discovered the elements some years later, and one-on-one. It was like a one-on-one or damn near map.
Can I interject something there about that? What you just said, Laura?
Yeah.
And correct me if I'm wrong about this, Mano. But my understanding of the periodic table is that what you just described about one chemical element is true of a large number of chemical elements that were all discovered after Mendeleev first envisioned and produced the periodic table. In fact, Mendeleev was able to identify and describe the behavior of somewhere in the order of a half a dozen elements during his lifetime after he came up with the periodic table. So what you're saying for that one element wasn't an isolated or unique case. That has happened multiple times.
Yeah.
Cool.
Yeah, Randy is absolutely right. And as I say, science works and it makes predictions and the predictions are borne out. That's not the issue. And true, but the point is that it makes its predictions based on the framework that it has constructed. And within that framework, it works. But there's no reason to think that that framework was uniquely determined from the beginning of time. If we had evolved, if the science had evolved differently, we may not have had the Mendeleev's periodic table. We may have had a different classification system that predicted different things, but it would still have worked. The question is, science works. Nobody is denying that science works. Nobody denies that it makes, and the reason when I say it works, it makes predictions that are borne out and borne out very precisely. But we should not make mistake precision for truth. As I said before, the human beings are very intricately constructed organisms. Make a slight change in the pH of your blood system and you would die. So we have evolved to become a very finely tuned biological system. But that does not mean that we are the only finely tuned biological system. There are other finely tuned biological systems. The entire species spectrum consists of finely tuned biological systems, which are different from us because they evolved differently. And we have no trouble accepting that because we see it all around us. And I'm saying, why do we think that the finely tuned scientific system that we have must be the only one that could exist? What basis do we have for that belief, other than the fact that it is all that we see and it works?
Natalie and Rich have a question. You want to go ahead and unmute?
I just did. Can you hear me?
Oh, hi, Rich.
Oh, hi.
Hi,
Mano. Yeah, it seems to me, I'm sympathetic with your meta theory. I find it very interesting, but I also feel it's not falsifiable. And I wonder if that bothers you.
Well, my early part of the talk was to say that falsifiable it never worked anyway. It doesn't work in science, it doesn't work.
I know that people love to say falsifiability is not valid, but it really, it's a powerful concept. And I can't imagine how I could ever prove to you that you're wrong. Because you use this tree of life as an analogy, and you point out that we have plenty of evidence of different branches of this tree of life. But you make the statement that we only have a single branch of the tree of science. How do you know it's a tree if you only have the single branch?
I don't know that for sure. But coming back to, first of all, the falsifiability, it is not powerful. In fact, pretty much all historians, philosophers, and sociologists of science have dismissed it. It doesn't work. And I spend an entire chapter in my book making the case why it doesn't work. I mean, it doesn't, I mean, let's face it, falsifiability doesn't work for many reasons, not least of which scientists don't even use it. For example, if you look at Newton's, as I said, Newton's theories, they were falsified for 60 years, but nobody ditched it. We kept it because it was a nice theory, and we don't want to throw away good theories.
I don't disagree with that, but there are uses of falsifiability. For example, the reason I don't believe in conspiracy theories is because when you talk to a conspiracy theorist, you never have any chance of convincing that person otherwise, because there's always an out. You can't falsify it. So in my mind, it's not even worth discussing.
But you can't falsify scientific theories either. Because as I said, how do you falsify a scientific theory? You say, well, it disagrees with experiment, right? But as I said, experiments consist of a package that includes other theories. And theoretical predictions consist of a package that consists of a lot of theories. So when they disagree, how do you falsify a theory? Because the problem could be anywhere.
So if that's the case, then what about phlogiston chemistry and what about ether?
Yeah.
Those were falsified, were they not?
No, they were not. What happened was the Einstein's, for phlogiston, when the oxygen theory came along, it made phlogiston an unnecessary concept. And so it was the community of scientists decided that we are not going to use phlogiston anymore. We're going to go with oxygen theory. With ether, when Einstein came along with his theory of relativity, he did not prove that the ether did not exist or falsify it. He just made it unnecessary. We didn't need the ether anymore, so we just ditch it. So the community of science decides, let's ignore ether.
But isn't it sort of the same thing? And this kind of ties over to the whole religion thing too. Doesn't probability of falsehood sometimes be as good as falsifying something?
No, probability is also, turns out probability doesn't work. And you can't prove that theories are more probable. Some theory is more probable than another. These are intuitive ideas that's part of what I would call the folklore of science. Richard Feynman had a good, in his book QED, he explained the origins of quantum electrodynamics in his book. And then immediately after that, he says, what I've just described to you is what I call the physicist's history of science, which is never correct. He said, it's just a myth story we tell our students, and our students tell other students, and pretty soon everybody accepts it, but it's not true, and we don't know what is true. And what I'm saying is that falsification is one of those myth stories that's very strongly held in the scientific community because it makes a kind of intuitive sense and seems most powerful. But we cannot falsify any theories, because if you want to hold on to a theory, you can hold on to it for as long as you like by invoking other auxiliary hypotheses. And Richard is right. It is similar to conspiracy theories. The difference is that scientific theories make predictions that can be tested. And it's the weight of that evidence that tells us that a theory is worth supporting. Conspiracy theories never make predictions that can be tested. They can always explain why something is the way it is, but they cannot say, because of my theory of this, this is what we expect to see. Or even when those theories work. Now, when the theories don't work, they don't add it to the weight of evidence. They just go on somewhere else. It's like, how many of you have heard of the Raelians? This religious.
Vaguely. Yeah.
They have this theory that life on Earth, life on Earth is caused by these extraterrestrial beings called by the name of Rael, extraterrestrial god-like, not a god, a human, naturalistic thing. But they created life in some other planet, and they developed the technology to create life and so on. But they didn't want to try it out on their own planet because it's dangerous. So they looked for another planet to test out all their theories. And they came to the Earth. And they came to Earth and brought all these organisms, and they created vegetation and so on. In fact, everything on Earth is the product of Raelian technology. Now, that's a wonderful theory. It explains every possible thing, but it's a useless theory because it doesn't make any predictions that can be tested. And that's the difference between science and all these other things, that science makes predictions that can be tested, and science works because those predictions by and large are borne out. What I'm saying is that the danger is going to the next step and saying that it works because it is true and it is the only theory possible, only framework possible. And I'm saying that that's next step is not justifiable. We have no reason to believe that that is true because the only thing we have on Earth is science on Earth.
But I thought over time, science sort of gets asymptotically closer to the truth, doesn't it?
Why do we believe that? Do you believe that human beings are getting asymptotically closer to a perfect human being?
No, it's the analogy.
What's the difference between the two?
I don't know, you tell me.
There is no difference. Just as human beings are not asymptotically approaching the state of perfect humanity, whatever that might mean, science is not asymptotically approaching any state of perfect science. We are just evolving. We are just changing and progressing. And that's, the question is, as Kuhn says, what do we gain by invoking this notion that there is some unique truth out there that science is approaching? What do we gain by that?
But can't we say something, okay, so the truth. Now, can't we at this point in time determine that, the sun is the center of our solar system, and that we are on a rocky planet that revolves around the sun at a predictable rate, and that the sun, our solar system is not the center of the universe, and so on and so on. Isn't it probable enough that these things are established scientific fact that we can consider them to be truth?
It depends on how you define truth and fact.
If something's true, it would be an objective fact that is demonstrably true.
It's
Or demonstrably provable. Let's put it that way.
okay. The idea of proof is tricky. So, for example, let's say it used to be thought that the celestial objects were perfect objects, and therefore they had to be perfect spheres, right? So, for example, before Galileo, they thought that the moon must be a perfect sphere because it's a celestial object. And then Galileo showed he used these telescopes that were invented in the Netherlands, and he used them to look at the moon, and he showed that there were imperfections on the surface of the moon. There were craters and stuff like that. It wasn't a perfect sphere. So what did the people who believed in the perfect sphere think? They said that it was a perfect sphere, but that the telescope had introduced the aberrations, that the telescope introduced distortions that made it appear as if the moon was not a perfect sphere. Okay. Now, how do you disprove that? Well, then you have to have a theory of telescopes to show that the telescope does not introduce aberrations, but instead just magnifies it. To do that explanation, you have to have a theory of optics, you have to have a theory of how the telescopes work, and so on. So now immediately you're bringing in other theories. And you might say, okay, we have established those theories. But then how do you argue with someone who says that, well, that's not the only theory. We also have the theory of how the eye works. What we see are just some signals that enter our eye and trigger certain electrical impulses in our eye that get transmitted along the neurochannels that goes to certain parts of the brain, and the brain reconstructs the image that we see. So when we see aberrations when we see distortions on the surface of the moon, that when you say we see that, it is a result of a complex network of theories that we believe in. That's what's called the unproblematic background knowledge. And we say, okay, we assume there's no problem with any of that. And therefore we can say that the moon is like this. But that is a judgment that we make. We decide to place greater validity on certain theories and the predictions of those theories than other theories. And that's fine. And science does that all the time, and it works very well. But never forget that what we are doing is choosing to prioritize certain theories over others. We are never forced to accept any particular conclusion. So when Mark, you say we know for a fact that we are orbiting around the Earth and so on, all that ultimately comes down to accepting certain theories over others. Karl Popper himself said that sense data, untheoretical items of observation, do not exist. Even our eyes, when we look at a telescope, we are using theories outside of us. But when we see something with our eyes, we are using a theory that's within us, which is the theory of the eye and optics. So it is hard to, in a sense, yes, it looks like we can't prove anything for sure. The difference, as I keep saying, that makes science so powerful is that it makes predictions, it works. We don't have to assume that it is true.
Matt has a comment. Go ahead and unmute, Matt.
Oh, I was just saying, to me, it sounds like a lot like language. The fact that any number of languages have developed over time that each have their own grammatical structure, and they use different intonations or whatever, and it can be very difficult to, even though you don't understand what this person in another language is saying, it works for them, it functions quite well. And switching from one language to the next, trying to learn another, it can be very difficult to wrap your mind around expressing yourself in a completely different way.
I think Matt is exactly right. The evolution of anything, language is a good example. Yes, and each language becomes more and more refined, its vocabulary increases, its grammatical structures change over time, and they evolve. And we have no trouble accepting that there are different languages, and they evolve according to different rules, as Matt points out. That's because we can see those. Because again, that's a purely an artifact of the fact that on the earth, we have different isolated communities where languages can evolve, just like biological systems can evolve. So therefore, we have no problem accepting that there are different biological systems, different languages, each of which is evolving and not evolving towards perfection. We are not saying that English is evolving towards some perfect English. It's just evolving. It's just changing. It's growing. It's diversifying. And other languages, just like. But somehow, when it comes to science, we are refusing to see the similarities. Science is evolving. Why do we think it's evolving in only one way, as opposed to language or biological systems? I know people find it hard to relinquish that idea. But as I was telling Marie earlier, it's a lack of imagination. It's because we have experience with only one. It's like fish in an ocean who may not be able to conceive of life outside of water.
Anybody else?
Is there such a thing as truth or reality then?
I have no idea. There may be, there may not be. What I'm saying is we don't know.
And yet Aaron Ross says that the truth is what the facts are. How supportable is that, do you think?
What does he mean by facts?
Facts is something that is verifiably true or inarguably true, or inarguably in alignment with reality as we observe it.
Facts, as I said in one of my slides, I didn't go into it in great detail, but a fact is dependent on the theories that you use to arrive at that fact.
Are facts, Lauren?
Yeah.
You think that when he says that he's also implying or stating implicitly or explicitly, and would you accept this, that facts are immutable? Because that statement, facts are immutable, is demonstrably false. Facts have changed repeatedly throughout human history.
Example,
it was considered a fact that the Earth was the center of the universe, and then everything revolved around that. That was considered a fact.
It was considered a fact, but it wasn't a fact.
But my
because
point
it was based on belief rather than observation and evidence.
No, it was based on observation, just not observations that are as good as the ones that we were able to make now. But it was based on observations.
Lauren, you might be. The question is, do you think that we happen to fortunately to be living at the time when we have finally got the facts right? That all the others before us was unfortunately not lucky enough to be like us and living at a time when we finally know what is right.
It's an evolving process.
Exactly. And that's what Randy is saying. The facts also change.
Yeah, but I'm sorry, a fact that does not align with reality is no fact to me.
But what I'm saying is you're just going around in a circle. Reality, and you're using reality and facts interchangeably and saying that one.
Yeah.
But I'm saying that, as I told
if a fact is not accurately descriptive of the reality that it is attempting to describe, of what use is it?
But how do you know what the reality is that you're describing?
Observation and evidence.
But then you're going around in a circle. Yeah. You're saying my observation is the reality, and that matches reality.
No, the interpretation of the observation is where the variation, the vagaries and everything else come in.
Can I suggest that reality and facts are actually not very useful concepts because they exist outside of our perception, because our perception develops, and that's what matters, rather than some quasi-objective idea of facts and reality. Facts are not a useful concept. Could I suggest that?
I feel just the opposite, that's why they are useful, because they are independent. What we may consider to be objective reality is indeed independent of our perceptions.
No, I think Rafiq is onto something. These are not very useful concepts. Well, what we have are descriptions of what we think is a reality, and the descriptions are all that we have. Some people give greater weightage to them and declare them to be objective facts. Others accept that they are conditioned on our perceptions and they could change with time.
So in other words, a fact, something that we may say is a fact right now, within 20 years, it may no longer be a fact.
Right, and that, as Randy said, that's what has happened over time.
Right.
Can I throw I just offer this without any commentary, but and I'll let you all discuss how you think this fits in there. But we're talking here about this idea of facts, as though facts are, at least some of us are, some people are, that facts are independent in some way of the theories that we use those facts to support. Charles Darwin, let me quote Charles Darwin. How odd it is that anyone should not see that all observations being a form of fact, must be for or against some view if it is to be of any service. So to say that facts are somehow objectively independent of the theories that are associated with doesn't make any sense to me.
Maybe.
The Earth is the diameter it is, and now it's, it can be demonstrated to be measured in several different ways. Does that fact not remain the same no matter what?
Yeah, but here's what you're doing. You're kind of cherry picking. You're picking one fact, and I'm not saying that there aren't facts, and I don't know if Mano would agree with this or not. I'm not saying that there aren't some facts that we are justified in thinking that we pretty much got it nailed down. Okay. Although if you're being a true critical thinker, in science, we never say that we know anything with 100% certainty. What we have is some level of confidence about how accurate it is. Okay. And there are some facts that we can be so confident of that we can treat them as though they are absolutes, although they may well not be. We won't know until some future date. So you just picked one of those. But you can't use one fact like that and assume that all other facts fall into that exact same narrow category there. There are lots of facts that right now that we should think that there's reason to think that, this fact may actually turn out to be wrong.
I think Randy's right. I mean, I deal with this in my book too. Sorry to plug the book, but this is important. There are certain things that we have direct sensory experience of. This desk in front of me, I treat it as a fact. But most of our knowledge is not the result of direct sensory experience. Most of them involve long chains of inferential reasoning using complicated equipment, especially scientific facts. I mean, how do we know that an electron exists? It's a long chain of inferential reasoning involving highly sophisticated equipment that produces raw data that is analyzed by experts and so on. And at the end of all that, we come to the conclusion that there is this thing called an electron, or that there is a proton, or there's a hydrogen atom. But that is not the same as saying this desk is in front of me. So in order to arrive at the fact of an electron, you have to accept all the theories and the interpretations that went into creating the electron. And one could argue that the electron is actually a metaphor, because no one has actually direct sensory experience of an electron. We have never seen it, touched it, or felt it, or anything. It's a metaphor that powerfully explains a vast number of things. And we can predict things using it. So therefore we accept it as a fact. But it's not a fact in the sense that I say that my table is a fact, as Randy says. There are different facts have different statuses. Mark, do you agree?
I'm afraid you're going to come back in 2 weeks and tell us everything you said today is wrong.
I doubt that, but why? I'm saying that everything I say is probably wrong. I mean, given that all scientific theories have changed over time, we can safely assume that the theories we believe now are probably wrong. Otherwise, we have this sense, sort of highly serendipitous, that we happen to be living at a time when we have finally got the right theories. How lucky is that?
I wonder if people living 100, 150 years ago thought that too at their time.
Oh yeah.
Right?
Oh yeah. In fact,
Yeah.
Kuhn says one of the things about science is how at any given time, the scientific community is so confident, so assured about the rightness of its theories. And in a sense, that's not a bad thing. I mean, that's what enables them to act with confidence and make predictions and go out. But you're right. It is people at any given time, we now think that the scientific theories we have are the right ones. Just as 100 years ago, they thought they were the right one. And 200 years ago, they thought they were the right one.
Just think in terms of, this is one that I used to teach when I was teaching. I used to use for illustration purposes, the history of the evolution of our understanding of the atom. If you go back to the very first model proposed for what the atom looked like, its structure and its composition, and then you see the progressive changes in that. Some of the scientists who made some of those proposals made the proposals in a kind of a tentative fashion. Others of them were pretty darn certain they had it nailed. But all along the way, the scientist, as Mano was talking about, you had individual scientists who made certain discoveries, and scientists are humans, so you get invested in an idea that you happen to generate, so you can kind of doggedly hang on to it sometimes. But our understanding shifted because as we learned more about it, the scientific community shifted. And if an individual scientist didn't shift with that community, then they basically ended up on the fringes of the science that they helped to develop.
Any other comments?
Do you know anything about artificial intelligence?
Nope.
Oh,
I do know one thing. It's 25 years away.
How can you be so sure of that date?
Artificial intelligence is always 25 years away.
Oh, okay. All right.
I was just wondering if machines someday might get to a point beyond Kurzweil's singularity, where the machine might do science itself, do what a scientist does in doing science, rather than just analyzing data. I was wondering if you thought that there might be a machine someday that could actually do what a scientist does.
I think Marie is probably in a better position to answer that kind of this highly imaginative question. I don't really have such a good imagination. I know the limits of my imagination. So I think that, but I am not the kind of person who can envisage a completely different scenario. I just feel that what we have can't be the only thing.
So it seems like you were saying repeatedly that science works. So if I came up with a theory that the reason the earth spins around the sun is because there's a spirit, a God that's holding it in place, that could describe why the earth is in place, and that would at some level work, wouldn't it?
No. When I say works, it makes predictions that can be tested. So what would your spirit predict?
I would say that I would look at the facts and make my God conform with the observed reality, and in that level, my model might work.
No. When I say works, it means it makes predictions that can be tested, and the results bear out the predictions. Your model is like the Relied predictions. The Relied theory, it explains everything. Because all it says is that there is these extraterrestrial beings that created life on Earth, and we are all the products of that process. That's not what works means. Remember, it has to be naturalistic and testable. And testable means you have to make predictions that can be looked for. You can't say it explains things.
Okay.
As they said,
is your meta theory testable?
I'm not claiming it's testable.
Oh, okay. So it has to be testable to be valid science, but your meta theory.
I'm not saying that my theory is science. I'm saying it's a plausible explanation. I'm definitely not claiming it's science. The only way I can test it is if we met up with some extraterrestrials. So in a sense, it's testable in theory, but in practice, we have no control over it because we have to meet the thing. So it is testable, quote unquote, just like dark energy is testable or something like that, but we haven't yet devised a way to how to do it. But your theory about spirits driving the universe, what does it predict? Does it make a prediction that we can test? What I'm proposing is a way of looking at science that explains history and suggests that there may be alternative things. I'm suggesting a metaphor for viewing science.
So what have you presented this to any like peer groups or anything? Is this something you've just recently developed, or?
I mean, that's what the book is, and so it's been reviewed by people, about 4 different people who review the book. So, because Oxford University Press, they send it out to academics to review it. I mean, to some extent, what I'm saying is controversial only to people who are not familiar with the literature in the history and philosophy and the sociology of science. If I was talking to philosophers or historians of sociology of science, they would say, oh, so what else is new? You know, they are familiar with these ideas. It's the science.
I think what you're saying, Mano, is descriptive.
Yes.
And that's all. It's a description of the way things are, and a very thought-provoking description it is too. And I'm going to read your book even more carefully now. But one thing I'd like to bring up is that we're living in very strange times now, and I think that we need to take a more radical view of the way that we live. I mean, for example, this Zoom meeting, we would not have had this type of meeting before because of the pandemic. And I think that it's a marvelous thing. But I think also even this doesn't only apply to the scientific world, but to the political world, the decision-making world, and which was why I was bringing up the question of what the consensus community is. We now have to think very carefully about what education is, how we're going to, what it means, how it's going to be delivered, how universities are going to work, how schools are going to work, what is about travel, about all sorts of things. And I think that this, that your idea about what actually works has also some relevance to the political world as well. And I'd like your comments now.
I think what works is a good framework for looking at things, because we are engaged in all kinds of ideological battles with people. For example, vaccinations, and some people oppose vaccinations. So what is the case for vaccinations? Because it works. I mean, we can point to things. Now, what do we mean by it works? Well, statistically, it eliminates a lot of diseases. It reduces the severity of diseases and so on. And whereas people who have agendas against vaccination will point to cases and say, well, this person got vaccinated and died 2 weeks after, or something like that. And then you have to ask yourselves, from their point, they are actually using what I would call the falsification model. They're saying that because they could find some data point that contradicts the scientific consensus, therefore they have invalidated the scientific consensus. They are essentially exploiting the popular notion of falsification to say that because they have this contra data point, that the theory or the consensus is not valid. We have to fight against that by saying that that's not how science works. Science works by consensus view, and the preponderance of evidence is in favor of something, not that every single event conforms to it. So I believe that we have a better case of fighting against these anti-science agendas
like in climate science denial or vaccinations or anti-evolution, if we move away from this idea of that science is true and false, because if we say that science is true and is true, then somebody who points to some contra evidence can say, well, therefore it's false, because if it was true, it would be true always, but now it isn't. So what I'm saying is, by showing that it works by means of a preponderance of evidence, we can say, yeah, you have found some evidence, but that doesn't prove anything of your case, because you have to develop a preponderance of evidence proving your point or in support of your point before the consensus will shift. As long as you have just this or that data point, it doesn't help you.
Not only did we have, or do we still have, Rafiq all the way from Bogor, Indonesia. We had our friend Muhammad Idris beam in for a while from Islamabad, Pakistan.
Wow.
But he couldn't get the, he could see everything, but apparently couldn't enable the video. I don't know if that's something maybe in his country, the Zoom features are blocked or something, I don't know, but anyway, I just thought I'd throw that in.
Well, I'll go ahead and stop the recording now. I think we've pretty much concluded our discussion, right?
Yeah. Mano,